Guys, this is Mr. Mellor. This is a help video for lab number 5. In case you're struggling, you're welcome to watch this, and we're going to work through it together. So for part 1, what you're going to do is go ahead and follow this link. It's going to pop up with 4 different icons. Make sure to click the motion icon, and you're going to end up in this simulation, which you can see on my screen. Okay? After you've done that, go ahead and make sure to click all of the icons in the upper right hand corner. This is just going to give us some numbers so that we can determine what is going on by using numbers to definitively say that there's in fact a relationship here between acceleration, force, and mass. Alright, so this first one, we're looking at Newton's first observation. That's part 1. It has to do with the relationship between force and acceleration. That was Newton's first observation, which was if we increase the force on an object, that's going to increase the acceleration of an object. Okay, so that was our example from class. Was you have a little kid with the baseball bat, he hits the baseball really hard, and with a big force, it causes the baseball to accelerate. It goes from a speed of 0 to a really fast speed in a short amount of time. So a big force makes a big acceleration, whereas we have our cute little cousin who's got a plastic baseball bat, and if he hits it, he doesn't hit it as hard, so a lower force, lower acceleration. And so we're going to see that, and the way that we're going to see that here is that we're going to look at our speedometer, and the final speed is going to give us an indication of the acceleration. So why can we use the final speed? Well, in this case, it's easy to use the final speed because our object is starting at rest. It's not moving. Its initial speed is 0. And so the final speed after, say, 10 seconds will tell us a lot about what the overall acceleration of the object was. Okay, so first step, what we're going to do is we're going to apply different forces to this 50 kilogram box. All right, so we're going to start off with 50 newtons. We're going to observe, it says observe the motion of the box for 10 to 15 seconds. We want to watch how fast the speed changes. So I'm going to go ahead, and I have my stopwatch open, which is from Google. If you want to use your stopwatch on your cell phone, that works as well. But I'm going to press this right arrow to set our force to 50 newtons. Okay, and we're going to keep an eye on the speedometer right here. I'm going to press start on our timer first, then I'm going to press go. All right, so after approximately 10 seconds, we're going to press pause. All right, so this is 50 newtons. All right, it's been 10 seconds roughly. All right, so 9.3 meters per second. All right, so remember that, 9.3 meters per second. That was a force of 50 newtons on our box. All right, so we're going to press reset. We're going to do it the same thing again. We're going to go with 100 newtons. We've checked all the boxes. We're going to go back to our stopwatch, press reset. I'm going to go ahead and press start, and with 100 newtons, we're going to see what the speed is after approximately 10 seconds. All right, so after approximately 10 seconds, went a little bit over, we had 17.7 meters per second. And so when we had 50 newtons of force, a push of 50 newtons, and newtons is how we're quantifying force, with a force of 50 newtons, we had a speed initially of approximately 9.3 meters per second after 10 seconds. When we had 100 newtons applied, we had a final speed of 17.7 meters per second. And so I think you can already start to see this relationship we're building, which is if the mass is the same, we're pushing a 50 kilogram box in both scenarios. If the mass is the same and you increase the force, that object's going to accelerate faster. And remember, acceleration is the change in velocity over time. So it picks up speed faster if you increase the force. Intuitively, that makes a lot of sense. All right, so we're going to do one more. Let's do 200 newtons this time. All right, so 200 newtons. We're going to skip the 150 in the interest of time. We don't want to have the world's longest video here. So press start. Now we're going to go to 200 newtons. Let's make sure we see our values. Okay, after 10 seconds, we're going to go ahead and press pause. All right, it's been approximately 10 seconds. And so we ended up with 36.4 meters per second. And so the final speed, when we had the greatest force, was the fastest. Okay, and so intuitively, again, that makes sense. That's our cousin who hits the ball really hard, the baseball really hard with his bat, and it zooms off faster than our other cousin who hits it really softly, and the baseball doesn't zoom off as fast, okay? And so what we saw was with 200 newtons, we got a final speed of 36.4 meters per second after 10 seconds, whereas with 50 newtons, we only had a final speed of 9.3 meters per second, okay? So if we think of track and field and we're trying to run outside, if you had the ability to push with a great force, say you had really big muscles, you would be able to get your object you could accelerate yourself by pushing on the ground really hard much faster. And so, Mr. Mellor, intuitively that makes a lot of sense. We know that bigger, stronger athletes tend to push or punch harder. That makes sense, sure. But we can use this idea that applied force causes acceleration to our advantage. Say, if you were to do a tug-of-war game against Dwayne "The Rock" Johnson, who's our favorite action hero, we are smelling what he's cooking, we love him, and he was on top of ice, a very slippery surface, whereas you were, even though you were maybe not as strong as Dwayne "The Rock" Johnson, maybe some of us are, I certainly am not, if you were going against Dwayne "The Rock" Johnson and he was on a slippery surface, he couldn't apply much of a force at all against that surface, so he couldn't pull very hard, whereas if you were not on a slippery surface, you could probably beat Dwayne "The Rock" Johnson, and so you'd be taking advantage of this portion of Newton's second law, which is the applied force is directly related to the acceleration. Okay, so question 1 is, what happened to the rate at which the box picks up speed as you increase the net force on the object? So I'm not going to write these out. I'm just going to talk about them because it's up to you to answer these questions. But what we have is the rate at which the velocity changed increased when the amount of force increased. Okay? And so the rate at which velocity, second sentence could be the rate at which an object changes velocity over time is called acceleration. So we said the rate of velocity change increases if force increases. It decreases if force decreases, and we call that acceleration. All right, so question 2, what does this observation tell you about the relationship between the external force applied and the object's acceleration? Well, this observation, what we just saw, is that when the total force is increased, then the acceleration increases. When the total force is decreased, acceleration decreases. Okay, so please write that in your own words. All right, we're going to move on. So the second part has to do with the relationship between mass and acceleration during a constant force. And so go ahead and press reset. What we're going to do is we're going to change the mass on the skateboard now. So we're going to start with the little girl. Go ahead and drag the little girl. So this is step 3. Then we're going to set the force to 50 newtons. And we're going to use 50 newtons every single time. We're going to hold our force constant, but we're going to change our mass. And so the second observation that Newton had, creating his second law of motion, was that mass acceleration is inversely proportional to mass. That means as acceleration goes up, mass goes down. All right, and so what we're going to do here is we're going to apply 50 newtons, a constant force, but we're going to change our mass, and we're going to see what happens to acceleration. Okay, so we've put the little girl on top of the skateboard. We've checked all of our boxes in the upper right-hand corner. We're going to go ahead and step 4 says to record for 10 seconds and look at the final speed after 10 seconds. All right, so I'm going to go ahead and press start. We'll give her a push of 50 newtons. Press start and start over here. Then after 10 seconds, we're going to press pause. All right, so we had 15 meters per second. Okay, and so after we've done that, we're going to go ahead and record this value in table 1 as the final velocity. All right, so 15.0 meters per second. Okay, and we're going to go ahead and calculate the acceleration. So we're using our initial version, our initial definition of acceleration, which is the change in velocity over time equation. We're going to use it from right here, step 6. It says to calculate the acceleration for all the objects considered. So we have final velocity minus initial velocity is divided by time. Well, our initial velocity is 0, So the acceleration is just going to be 15 divided by 10, which equals 1.5 meters per second squared. Okay, then step 7 says we're going to calculate the acceleration using Newton's second law, which is acceleration equals force over mass. And so we're going to say the force applied is 50 newtons, and the mass is 40 kilograms. And so 50 divided by 40, what is that? 50 divided by 40 is 1.25 meters per second squared. Okay, so those look very similar. And why would they not be exactly the same? Well, remember, we are personally going through and we are using our timer, and so we have some error ourselves in pressing the timer at the right time, making sure we're actually measuring the acceleration for 10 seconds, etc. And so some human error is causing our values to be off. But if we were able to enact this simulation perfectly and human error didn't come into the case into play, then these numbers would be exactly the same. So the acceleration should be 1.25 meters per second squared. All right, let's do one more, and then the remaining 3 will be on your own. So press reset, then you're going to go ahead and check all the boxes. Okay, drag the, well, actually we're keeping the crate, so keep the crate up there, and we're going to go ahead and go back to the stopwatch. We'll press reset. I have it on pause right now, so we can set the force without worrying about the thing taking off on us. All right, 50 newtons. After we set 50 newtons, we're going to go ahead and press play. We'll get our stopwatch going, and after 10 seconds, we're going to press pause. All right, and so we've increased the mass with the same force, so we're thinking that the acceleration overall should be less. Okay, so I went a little bit too far. I missed when I pressed the button, but we're going to say that we're going to round that to 13.0 meters per second. We had 14 right there. Let's do our calculation. Acceleration is equal to the final velocity minus initial velocity. So that's 13 minus 0, which is just 13, divided by our time, which is 10 seconds. And so we get 1.3 meters per second squared. Okay, let's do our final calculation. Acceleration is equal to force over mass, net force over mass, 50 newtons divided by 50 kilograms. Why 50 kilograms when we use 40 in the last one? Well, that's given from our table. So we get 1.0 meters per second squared. Okay, and then you're going to do the exact same thing we just did for the first two for the rest of the table. Okay, so we used equation 1, which is shown right here for step 6, and then equation 2, which is shown in step 7 for this portion of our column. All right, so we have part 2 guiding questions. What did you notice about the acceleration values obtained by the different items? What do you think caused the variation in these values? So why did the acceleration change? Well, the acceleration values were different because the mass was different. We had the same force applied, but the mass had changed, and so the acceleration values had changed. And so the variation was caused by the fact that if you keep the mass the same and if you keep the force the same and you increase mass, then Newton's second law tells us that acceleration will decrease. Similarly, if you keep the force the same and you decrease the mass, then the acceleration will increase. Okay? All right, next question, question 6. What variables can you manipulate in the simulation to get all the items get the same approximate values for the acceleration? Well, think about it this way. We had acceleration is equal to the net force divided by the mass. We had the case where we had a constant force applied to all of these situations. Well, we know that we can hit things harder or push things harder or softer. And so even though we've been holding force constant, we could actually still change that. So the variable that we could change in this case would be force. So if our overall relationship between acceleration and force and mass is acceleration is equal to the force over the mass. Remember, we had two observations that led to this overall equation, acceleration equals force over mass, and those two observations was acceleration is directly proportional to force and acceleration is inversely proportional to mass. Okay? All right, so the variable that you could change would be force. And then This would allow all items to get approximately the same acceleration because regardless of their mass, you could just push harder and harder with the bigger objects to end up with the same acceleration. Would you have to push really hard to, say, get a refrigerator to accelerate at the same speed as a little girl? Yes, you would have to push really hard, a big force, but you could still do it. All right, question 7 and question 8 and question 9 and 10, I'm going to leave those to be up to you because they're kind of a test of your knowledge based on what we just did. Question 10, you have the choice between 6 options of what you want to do to show your understanding. Please, for question 10b, you're going to self-assess, choose what you think you deserve for your product that you make, and highlight that one of those boxes, okay? I'm going to post some resources to help you with these options, but choose the one that appeals to you, that you think would allow you to express your knowledge the best, okay? All right, that's the end of our help video. Have a good weekend, guys. I will see you in class on Monday and Tuesday, all right? Don't stress. Life is good. Life always gets better, or at least in the long run it will, okay? So persevere. You guys are doing awesome. All right, bye, guys.